Hello everyone, I am Hao Shen from Peking University, and I'm glad to represent our team ICLR to present our work, Learning Category Level Generalizable Object Manipulation Policy via Generative Adversarial Self-Imitation Learning from Demonstrations. First, let me introduce our team. We are from Embodied Perception and Interaction, in short, ICLR, led by Professor He Wang at Peking University. Our team members include me and Wei Kang, who contribute equally to this work along with He Wang. We won the first place in the No External Annotation track of Many-Skill Challenge, where we are allowed to interact with the environment and provided with demonstrations. We also outperformed the second place by a large scale. Based on the challenge, we proposed a novel category-level imitation learning algorithm to learn a generalizable policy that can work on unseen test instances from given object categories. To ensure that our method can be applied to general imitation learning problems, we at first don't assume handcrafted dense rewards are available and only assume a terminal reward. We then couple generative adversarial imitation learning, or GAIL, with SAC as our baseline to utilize demonstration data provided by Many-Skill benchmark. In this baseline, GAIL utilizes an adversarial trajectory generation scheme. It comprises a generator, which is the policy network of SAC, and a discriminator DeFi. This discriminator trains to distinguish between expert trajectories tau E and generated trajectories tau G. It also provides dense rewards RT to SAC. This off-policy imitation learning framework also contains three buffers: replay buffer BR, generated buffer BG, and expert buffer BE. On top of GAIL with SAC baseline, we propose three important techniques including the progressive discriminator, the generative adversarial self-imitation learning from demonstrations, and the category-level instance balancing buffer. Next, I will introduce the three methods respectively. The first challenge we met in GAIL is that the discriminator in GAIL is too strong. Due to the need to handle many training instances with large variations, the policy network struggles to ramp up at the very beginning and can easily be overpowered by the discriminator. Here the figure shows how the reward from the discriminator changes over training. Basically, it quickly diminishes to zero and leads failures in imitation learning. The issue is, how can we balance the generator and discriminator? Inspired by progressive growing gain and curriculum gain, we propose to progressively grow the architecture of the discriminator of GAIL during the training to alleviate the imbalance. More specifically, we let the discriminator evolve from a simple initial architecture, which is the point net, to a more complex one, the point net plus transformer. In this case, the discriminative power is gradually increased. Note that we won't evolve the architecture of the generator because the output of our policy network is always in the same action space without any change, which is different from the progressive gain. And the issue mainly comes from the overpowered discriminator. We want the policy network to be as strong as possible from the very beginning. Leveraging the progressive growth of the discriminator, we observe a significant increase in the reward throughout the entire training. However, the reward from the GAIL still tends to decay. This means the discriminator can get easier and easier to tell apart our generated trajectories from expert demonstrations. We want to know why. Our diagnosis shows that this decrease might originate from the clustering phenomenon in the trajectory space of expert demonstrations. Since the demonstration provided by Many-Skill Challenge is obtained from per instance RL training, the underlying manipulation strategies can be quite different for different object instances. This figure shows a t-SNE visualization of the global feature extracted by the training discriminator, where one color refers to one object instance. Our generator tends to learn a continuous function across different object instances and therefore has intrinsic difficulties to mimic this clustered distribution. Inspired by GESIL and ICLFD, we update the expert buffer with the successful trajectories generated by our own policy network, which is so-called self-imitation learning algorithms. This helps our policy to do well at the beginning of training and learn a more universal trajectory during the later training process. Compared to, per instance, RL policy, our policy network tends to learn a more universal trajectory that can handle different object instances in a similar way, which comes by nature from the continuity of neural networks with the change in object instances. This figure shows the Disney visual comparison of the global feature extracted by training discriminator and one from initial data in expert buffer and one generated by our policy network. The downside of using generated successful trajectories to fill expert buffer is the Matthew effect, which makes some objects instance happen to succeed very earlier than the others, so they dominate in the expert buffer, thus leading to an uneven distribution among all object instances, making the harder instance even harder to handle for the policy network. So we propose a constant slot for each object instance, so the number of trajectories for all instances are the same as shown in the figure. We call this category level instance balancing, or CLEAP expert buffer. Although simple, this design is essential to avoid overfitting a small number of instances and thus ensure the generalizability towards novel test instance. This picture shows success rate comparison of some varied instances before and after using our CLEAP expert buffer. In the open cabinet drawer task, the handles of cabinets have many variations, and some handles, for example, the nail-shaped, are hard to be opened. Without CLEAP, the expert buffer will soon forget the initial demonstrations for these instances, and the agent will not learn to finish these tasks. However, with the help of CLEAP, the expert buffer always reserves demonstrations for these drawers, so that the agent also gets some successful knowledge on these instances. The main results are shown in this figure, with progressive growing of discriminator, self-imitation learning from demonstrations, and CLEAP expert buffer. Our method combining the three techniques outperforms the baseline Gale by 13% and 18% average across 4 tasks on training and validation sets. Also, from this figure, we can analyze the effect of one particular technique. For meta-skill challenge, we further leverage the dense rewards provided by the original paper. We find that our methods with additional dense reward, which ranks the first place on the no external annotation track of meta-skill challenge 2021, can outperform the Gale baseline by 7% average across 4 tasks on both training and validation sets. In summary, our proposed techniques exactly pinpoint the bottleneck in category level imitation learning and thus yields significant performance improvement. We have all open sourced our project and welcome to visit our project page and GitHub repo. Thanks for watching.